For many years, the most common way computers displayed information on a monitor was through this ubiquitous VGA interface. But how does it work? What electrical signals does a computer need to send into this thing in order to get a picture to show up? Now, this connector has 15 pins, but aside from some grounds here, actually a bunch of these pins are ground, there's only 5 signals that we really care about. There's red, green, blue, horizontal sync, and vertical sync. Some of these other pins are sometimes used in different ways for the computer and monitor to communicate about what resolutions the monitor supports and things like that. But those are all optional, so we can just ignore everything but those 5 pins. And the way this works is pretty closely tied to the way old school CRT monitors worked. In those old monitors, you had an electron gun pointed at the screen with electromagnets around here that could deflect the electrons to different parts of the screen. Then to paint an image, the electron beam just scans across the screen from left to right and top to bottom. Of course, that's not actually how it works in a modern flat panel monitor, but the timing of that electron beam physically sweeping across the screen is still what defines the timing of when we need to send each pixel. And we don't just need to worry about the order of the pixels and the time from one pixel to the next. There are also these margins on the top and bottom, left and right, for the electron beam to sort of have a chance to stabilize or kind of think of it coming up to speed before it paints the next scan line. Then it blanks and has a little extra room on the right here before the beam swings back to the left, which also takes time for the beam to swing back to the left to start the next scan line. And then same thing at the bottom of the image, there's some blank scan lines down here before the beam gets sent back up to the top left for the next frame. And so there's this physical process that the timing is based on. So even though a more modern monitor doesn't use the same physical process, we've got to follow the same timing in order to get an image to show up. And so this diagram shows the detail of what that timing looks like. The visible part of each scan line takes some amount of time, and that's followed by what's called the front porch, which is just the blank time on the right side of the image. Then you get the sync pulse, which is a separate signal line, this horizontal sync signal, that tells the electron beam to swing back to the left side of the image. And then the back porch is the blank time on the left side of the image before the next scan line starts. And then it's the same at the end of the entire frame. So you get to the end of the frame, there's a front porch, which is the time to account for blank scan lines down at the bottom of the image. And then a vertical sync pulse, which is the signal and also the time that it takes for the electron beam to get sent back up to the top left of the display. And then there's a back porch, which accounts for blank scan lines that are at the top of the next frame. But what matters here is that for any particular display resolution a monitor supports, we've got to get these timings right. So the horizontal sync and vertical sync signals are pins 13 and 14 on our connector here. We've got to get the timings of those signals right in order for the image to show up properly. And in fact, with older CRT monitors, if you didn't get the timing right, you could actually damage the monitor because you could get the electron gun pointing somewhere where it shouldn't be pointing. And I don't think it's possible to damage newer flat panel monitors, but if you do end up damaging your monitor, I don't want to hear about it. Don't blame me. Actually, I do want to hear about it, but don't blame me. Okay, so getting the timing right is important, but what are the exact timing requirements? Well, if we look up VGA signal timing, you can see in this first link, there's a whole bunch of different resolutions and different modes. And a good video card would support a bunch of these resolutions and maybe even communicate with the monitor over some of those data pins I said to ignore to pick the best mode. But my goal is not to make a good video card. My goal is just to get something working. So, I'm looking for one of these modes, any mode that I think is going to be easiest to build hardware for. And, there's a bunch of trade-offs, so depending how you think about it, you might come up with a different choice, and that's fine. But, I figure I want to avoid the larger resolutions here because that's just a lot more image data to worry about. And then I'm just looking at the different pixel clock frequencies here, since I'm going to need to build a clock that runs at one of these frequencies. And these are all in the tens of megahertz, so that probably means using a crystal oscillator of some sort. And I've got a bunch of crystals, different frequencies, and of course none of them are any of the frequencies we want. And I also have some of these integrated crystal oscillator can things that you can just hook 5 volts up to and it spits out a nice clock. In this case, this one's 10 megahertz. But unfortunately nothing I have matches any of these clock frequencies. However, I can actually use a slower pixel clock as long as I compensate by sending fewer pixels. So for example, I could use that 10 megahertz oscillator here instead of the 40 megahertz pixel clock. But of course, timing is still critical. I can't change the overall timing. But the times that matter here are these times here, and they're based on the pixel frequency, but they're also based on the number of pixels. Right, because what really matters is how long does it take to draw each scan line? How much time do we spend in the display? How long is this front porch? How long is this sync pulse in terms of time? And so forth. And so that's what matters, and that's what these times are here. So this 20 microseconds of how long it takes to draw the visible area of one scan line is based on having 800 pixels divided by 40 million pixels per second, and that's 20 microseconds. But if instead of a 40 megahertz clock, we're using a 10 megahertz clock, well, 200 pixels divided by 10 million pixels per second is still 20 microseconds. And so the timing will still work out. And then same thing with the front porch, the sync pulse, and the back porch, right? Because if our front porch, we get to 200 pixels here, and we keep going another 10 pixels, well, 10 pixels divided by 10 million pixels per second is 1 microsecond. And so that front porch will take the right amount of time. And then same thing with the sync pulse. If we just keep counting another 32 pixel times, 32 pixel times divided by 10 million per second is 3.2 microseconds. And so our sync pulse will be exactly the right length. And so as long as we divide all these pixel numbers by 4, and conveniently they're all divisible by 4, we use these numbers, our overall scan line is still going to take 26.4 microseconds, even with this 10 megahertz clock. So that's what I'm going to do. So I guess to start out, what I'm going to do is build a circuit that's going to count pixels, because we need to know where we are. We need to know, are we at pixel 0? Are we at pixel 50? When do we get to pixel 200? When are we in this range here where the sync pulse needs to be low? So to do that, I'm going to build a counter that will just count pixels, and then when it gets to 264, we'll reset it, and that'll count the pixels horizontally, and then we'll end up building another one to count where we are in terms of which line we're on. And so to count the pixels, I'm going to use the 74LS161, and because we've got to be able to count all the way up to 264, that's going to take 9 bits. And the 74LS161 is a 4-bit counter, so in order to get at least 9 bits, I'm going to need 3 of them. So I'll start by connecting the power and ground pins for each one. So then we'll just kind of go through each of the pins and hook them up. So the clear pin is what's going to reset all of our counters to 0. So we want to be able to clear all of them at the same time once we get to 264. So I'm just going to tie the clear pins together for now. And then the clock pin is kind of the same way. They're all going to use the same clock, so I'm just going to tie the clock pins together for now. And eventually I want to connect that clock pin to our 10 megahertz oscillator, but I'm going to leave it out for now just because in order to test it, I want to be able to run it at a slower speed to start with. So next we have our data inputs, and we're not going to use that because we're never going to load a value into this. We just want this to count. So I'm just going to leave all those disconnected. But the enable pins we do want connected, so I'm going to connect them all high so that the chips are always enabled. And again, because we're not using these inputs for anything, the load pin over here, we don't want to use that either. That's an active low, so I'm going to tie them all high. And then this other enable pin, this enable T, I'm going to enable the first one, but the other two I'm not going to always have enabled because this is actually how the ripple carry works. So we're going to count the first 4 bits on the left here, and then we want it to roll over and count the next 4 bits here and then roll over and so forth. And so the way that works is we connect the ripple carry output of the first chip to the enable of the second chip, and then the ripple carry output of the second chip will connect to the enable of the third chip. And that way we've cascaded these together so that we will be able to count actually 12 bits because there's they're 4 bits each, but we really only care about the first 9 bits. And so that should be all we need in order to get a counter going. So what I'll do is connect the outputs up to some LEDs so we can see if it works. So there we go, we've got the first 10 bits, even though we only really care about the first 9 bits. Got the first 10 bits hooked up to those LEDs. If we power this up, well, nothing happens because we don't have our clock yet. If we just hook our 10 megahertz clock up, we're not going to see anything. This is just going to be counting so fast that it just looks like all the LEDs are on. So now for a slower clock, I could use a 555 circuit like I've shown in a previous video, but actually what I'm going to do is use this fancy signal generator since it'll give me a lot more control over the exact frequency. And so we want to set this up for a square wave, and then the high level will be 5 volts, and then we need to set the low level, that'll be 0 volts. So that way we'll get a square wave that goes from 0 volts to 5 volts. And then the frequency here is 1 kilohertz, and yeah, that seems fine. We'll start there. And so I'll hook the output of the signal generator up to our clock input here. So that'll go right into our clock for all 3 chips. And so now if I turn on the signal generator, and there we go. It looks like it's counting, but it's counting pretty fast. We can slow it down. Let's try 100 hertz. And that's not working as well. But you know what? Our clear is not actually, they're hooked together, but they're not actually hooked to ground or 5 volts. So I think ground clears it, but if we hook it to 5 volts, there we go. So it was just sort of clearing itself because that was floating. But now you can see it's counting in binary, which is what we want. And we can slow it down even more if we want to. But really what we want to be able to do is we want to be able to know when we get to these different time points here. So we want to start counting at 0, but then we want to know when we get to 200, we want to know when we get to 210, when we get to 242, and when we get to 264. And then actually 264, we want to reset it back to 0. Well, how can we tell that? Well, to figure out when the counter gets to 200, we're counting in binary, so this is going to be the binary equivalent here for 200. So all of the bits are zeros except for these three, right? We've got the 128's place, the 64's place, and the 8's place, and that makes 200. So we have these signals that look like this, those three ones that are set, and we want to be able to detect when we get here. What we can do is we can actually invert all the bits that are supposed to be zeros and not invert the bits that are ones, and then over here on the right, all of these are going to be ones when we get to 200. Then what we can do is we can just feed all of that into a NAND gate, and the output of that NAND gate will go low only when all of the inputs are high, and all of those inputs are going to be high, or all of those inputs are going to be ones, only when our counter over here is actually at 200. Now you may have noticed I only hooked up 8 of the bits. There's this 9th bit that's kind of hanging out up here. Well, that's because we can use the 74LS30, which is an 8-input NAND gate, but it's only 8 inputs. And as far as I know, they don't make a 9-input NAND gate. But that's actually okay, because looking at these 8 bits is actually enough to know that we've gotten to 200, because this 9th bit up here is the 256's place. So if that actually were a 1, and the rest of these bits were set the way they are, then the overall value would be 200 plus the 256 place would be 456. But remember, when we get to 264, we're going to reset our counter back to 0. So, our counter's never going to get up to 456. So we don't have to worry about this being a 1. If the rest of these are set the way that they are, then we know this is going to be a 0, since we're never going to go over 264. So it's fine to just ignore that one. So this will detect when we get to 200, and we can do a similar thing to detect when we get to 210. We just have to look at different bits, right, so to match the value 210 that we're looking for. And then same for 242 as well, same basic idea, right? We just have the bits that we're looking for, and we just put the inverters where we need them in order to detect that with the NAND gate. And then finally, this is what it looks like for 264. But now in this case, we do need to look at that first bit to make sure it's actually a 1. Because if this were a 0, the rest of these bits, this is the only other bit set, and that's the 8's place. So if this were a 0 up here, the overall counter value would be at 8, which we're going to get to 8 long before we get to 264, and so we would detect this early. So that's no good. We've got to make sure that first bit is a 1. But in this case, it's actually okay to ignore the last bit here, right? This last 0, because if this value here is 264 and we change that to a 1, then it's going to be 265. But of course, when we get to 264, we reset back to 0, so it's never going to get to 265. So whenever these first 8 bits are set like this, we know the last one can't be a 1, so we don't have to check if it's a 0. So in all of these cases, we got lucky that we can kind of cheat and only look at 8 of the bits. Now, obviously, we've got a lot of inverters here, but a lot of them are duplicates. We really just need 1 per bit like this. So we've got the 9 bits coming in, and then we invert all of them. And so then we've got the inverted and non-inverted version of each bit. And then when we decode each of the numbers we're interested in, we can just kind of pick off the inverted or non-inverted copy of each bit that we need, depending on whatever number we're trying to decode. So this is what we need to build, and I'm going to start off with 9 inverters. So to invert each of the signals, I'm going to use the 74LS04, which has 6 inverters. We need 9 of them, so I'm going to have 2 of these chips. And so now I'll just hook up each output to the input of an inverter. Okay, and so now we have all of our outputs for our counter, all 9 bits anyway that we care about, hooked up to inverters, which means now we've got inverted and non-inverted copies of all of our counter signals over here that we can use to detect those 4 values we're looking for. So next we need to add those NAND gates, so I'll add another breadboard here where we can do that. And then here's the first 74LS30, which is an 8-input NAND gate that'll let us decode one of those values. And the first one I'll do is 264, because that's the one that also resets us back to 0, so that'll be a good one to have. So let's try to detect the number 264. So starting on the right here, the first bit is a 0. We actually don't care about that because remember, we're going to look at just the top 8 bits. So we'll just ignore the first bit. So the next bit's going to be a 0. So we'll hook up one of the inputs here to the inverted output of not the first one, but the second one. So that's our second bit is 0. And the third bit from the right is also a 0. So I'll hook that one up to our inverted output of our third bit here. Then the next bit's going to be a 1. So I'm going to hook that not to the output, but to the input of this inverter here. So that's just going to be the same as the output of our counter. And I'll hook that up to another input. And what I'll do is the inverted lines I'll use blue, and then for the non-inverted ones I'll use green. So it's sort of easier to tell what's what. That's a 1, and so then we've got 4 more zeros. So I'll hook that to the inverted output of the next bit. Then another 0 will go to the inverted output of the next bit, and then another 0 going to the inverted output of the next bit, and then 1 more 0, followed by that 9th bit is going to be a 1. So I can just hook that directly to the input of this last inverter, because that's connected directly over to this 9th bit of our counter. Alright, so we've got all the inputs of our AND gate hooked up there. suppose I should also connect power and ground for a new chip over here. And then the output is pin 8 here. Let me just hook an LED to that and see what's going on. And if I connect power, that's on. And of course that's on because this is a NAND gate, so the output's inverted. So that's going to be on unless we've got exactly the value 264 in our counter. So if we reset our counter here by tying our reset here to low and then back to high, we should have a 0 in our counter, so not 264. But if we send 264 pulses, then that LED should go out. And it's sending it, and hey, it went out. So there we go. We've detected our 264 pulses. And if we send one more pulse, so let's see, one more pulse, and we need to trigger in order to get to be able to detect 242. So we're not at 242 now. That's a good sign. All right, so we got the first two. We got the 264 and 242. So now we just need to do the same thing for 210 and 200. And so this is basically the same exercise. We're going to add another 8-input NAND gate and hook up all of the appropriate inputs so that it detects the number 210. And then again, we'll do the same thing with another NAND gate and hook up all the inputs for that so that we're able to detect the number 200. Okay, so now we should be able to detect all 4 of these numbers. So let's test it out. If I reset, we aren't on any of these numbers. We're hopefully at 0 because I just reset it. And now I'll send 200 pulses. And there we go. We got our 200. And now I'll send another 10 to get to 210. And now we're at 210. So I'll send another 32 to get to 242. That's 242. And I'll send another 22 to get to 264. And there we are at 264. And actually, when we get to 264, what we want to do is reset our counter so that we start back at 0 again. What I'll do is just hook the output of that over around to our reset signal. So now if I just let the clock run continuously, I don't know if you can see it, but these LEDs are flicking out very briefly. There they go. I'm not sure if you can tell on camera, but it's going through the cycle. So at 200, 210, 242, and 264, these LEDs are going off very briefly, just for one clock cycle. But what we really want is we want to be able to tell when we're in the different sections of this signal. So for example, we want to know, should we be displaying pixels or not? Or should we be sending the sync pulse or not? And so for that, what we really want is we want to know, are we between pixel 0 and pixel 200, or are we between pixel 210 and pixel 242? And right now, all we have is just a pulse when we get to each of those points. But what we can use is we can use an SR latch. And this is actually an inverted SR latch because our outputs here are active low, so we want the inverted set and the inverted reset. And if you want to know more about the SR latch, I've got a video on that, so you can check that out up there. But what we want to do is we want to be able to say, okay, when we get to 0, or actually which is the same as 264, because when we get to 264, we're going to reset and be at 0 right away anyway. So when we get to 264, we want to set this latch. And then when we get to 200, we want to reset it. And then our output Q will be high if we should be displaying pixels, and low if we're in the blanking section over here. And then we can use another SR latch for our H-sync, our horizontal sync signal. And in that case, at 210, which is that guy, we'll set the latch, and then at 242, we'll reset the latch. And then the Q will indicate whether our horizontal sync should be active or not, or actually, since this is a low going